Dr. Liu, could I just announce that we did set up a folder on SharePoint. Everyone should have access to it, and each week files are going in there, and Bashir posts the video as well. Cool. So if anybody doesn't know how to find it, it's on the ACF SharePoint shared documents. The folder title should be very explanatory.
We saw some Academy Award nominations for Professor Liu.
So, you know, what we're doing right now is just for fun, we're going to create a certificate for this class. And after you finish this class, I'm going to take a picture of you. There's going to be a, Grand Solutions University blockchain certificate. It's going to have your signature right there. That's signature of Michael course. And then we're going to put it inside the Grant University blockchain. So forever, it'll be stored. And now, since you're going to be able to control your data, if someone's like, hey, did you ever take that course? You can sort of say yes, you turn it on, or no, you don't want to turn it on. So you control your data. So if if someone's like, hey, if you have any blockchain experience, you're like, yeah, I took this certificate at Grant Solutions. They're like, okay, go prove it to me. You're like, okay, just go to this website and look me up. I'm there. That's following MIT. MIT did that. I thought it was kind of fun.
And if anybody tries to change that website, it invalidates the whole thing, right?
Exactly.
So yeah, I've been reading my book.
Yeah. Good.
All right.
So if anyone tries to change that, it's going to be forever there. So what I want to start out with is just to let you guys know what's going on right now. There's a consulting company that most of you guys know, McKinsey, and this just recently got released, Blockchain Beyond the Hype. What is the strategic business value? And so they're sort of discussing some of the stuff that we're discussing, right? And they're thinking about which industry is blockchain really going to affect, right? And so if you read this, it's kind of interesting. I just sort of skimmed it, but what I liked was this chart right here. And here you have different vectors, but on the y-axis, it's high impact versus low impact, right? So you want to go high impact. And then on the x-axis, it's feasibility, low feasibility and high feasibility, right? So you want to be in the upper right corner. So we look at some of these dots here. This thing is, you should get really excited because you know what the yellow is? The public sector, which is what we're in, right? And so the public sector can have a really high impact, high feasibility. I think Grant Solutions is just sitting right there ready because probably like
the new dog.
And then, so you can sort of look at where this is. This is financial services too. So financial services and the public sector are probably, I think McKinsey thinks is going to have.
Which one is the counterpoint there? The opposite example on the lower left?
Yeah, let's take a look at this, John.
Is that agriculture?
Arts and recreation.
Arts and recreation. Do you think that could be just because it's not, data-driven?
Maybe they don't know how to program those artists.
Is that what it is?
I mean, you could put your art creation, IP onto blockchains, but recreation, going outdoors and finding rocks or going hiking, right? And it's a little harder to sort of put that in a blockchain unless you want to prove that you did the hike or whatever it may be, right? So, things that we currently do, like swimming and, recreational sports, it's kind of like data that exists, but we don't really want to.
Yeah, maybe that one's not a good example. Like manufacturing. I was just trying to study what is a good example by thinking about the counterpoint. So what's that manufacturing? Is that other one just above arts?
I'm sorry, this one right here?
Yeah.
Yep.
Because I'm just, just trying to understand the chart, but it doesn't make sense to me because as a manufacturing, that's like quintessential data collection and, little tiny improvements to try to get to Six Sigma or something, right?
Yeah, absolutely. But, when you sort of think about it, there's a lot of digital assets in financial services, right?
Right.
Trading stocks, right? So that's perfect for being disrupted. And, there's a lot of data in the public sector that we're not really using.
Right.
Public data, so it should be available to the public, right? But how hard is it to sort of share your data, especially your public data? There may be some data that you don't want to share, obviously. But, think about, how much digital assets are here, how much digital assets are here, is there a lot of digital assets here,
Well, not that one. The manufacturing is the better. Yeah.
I'm not sure. This article is supposed to go through each one of these industries, so we can you can drill down into it. And, I think it's, I haven't spent too much time reading this, but I think, I will definitely put posted in there, read it, and we pause when I require reading reports when I do it in the business goal.
But you know what I mean, like, because the counterpoint example has to validate, the same hypothesis, right, in order for everything to be reasonable, right?
Also, we can be wrong.
Right. Well,
So,
I mean, maybe they're not earning their $1,200 an hour or whatever it is that they charge, right?
they definitely charge a lot to talk to them. All right. So anyhow, it's in the minds of everyone right now.
What's that?
It's a pretty hot topic, but their conclusion, at least their thing is talking about how it's a little bit early. We're very early. They think the horizon's about 3 to 4 years before we see the next, real big hit, right? Which means that someone is actually using the blockchain. It's very useful for everybody, right? So they haven't seen it yet. So today, what we're going to cover in this course and the next course and the next course, so the next 3 courses is the core of the blockchain. So you want to sort of attend, if you're going to attend any of this courses, probably this one, the next one, the next one, probably the most of it, because it's going to get very technical. But we're going to take it very slowly, and where there's a lot of exercises, we're going to do a lot of sort of hands-on stuff, so that you have a lot of intuition on what's going on here. And some of the stuff we're going to cover today, in particular, hashing is not something that anyone ever does on a normal basis. So we'll be we'll slow down there. We'll do some examples so you have a really good understanding of what hashing is, and then we'll move forward from there. Okay. So today we're going to start the introduction of how the blockchain works. First, we'll give you the overview, the macros, from beginning all the way to the end. We'll talk a little bit about how do we document ownership. Then we'll spend some time in hashing and hashing in the real world. So this section, there's a nice URL, and we're going to interact with it. Hopefully, you have a computer. Some of you that you can do it. I think it'll be helpful for you to really sort of understand these concepts. Like, do it. Okay, so do you guys have any questions so far? With classes or anything like that?
Just a quick question. I promise this time. I missed the last lecture. Was that the one that addressed, the importance of data integrity?
Yeah.
Okay.
Okay. That's right. So I think is there going to be video recording? Yes. Okay.
That's posted in chat.
Okay. So make sure you have access to that. Okay. Very good. So what is the goal here? Just to reiterate, to design a piece of software that manages ownership, because ownership is very important. You have purely distributed systems. So what does that mean? Well, anyone can sort of jump onto this network, and if you jump on the network, that means your computer is getting onto the network in a node, and now you're going to play by the rules or the protocols of this network, right? So you agree with sort of be part of it. It's a peer-to-peer system of ledgers, and why is the ledger important? Because this is going to track who owns what, right? So if I had a Bitcoin and I gave one Bitcoin to Mark, then that ledger is going to say, okay, you deduct Professor Liu's Bitcoin because he gave that Bitcoin to Mark. And now suppose that we give that ledger to everybody. Now everybody has a copy, right? So now no longer is there a question who owns the Bitcoin. Mark owns the Bitcoin, right? And I don't have the Bitcoin. Suppose I only have one Bitcoin. So if I try to send somebody else a Bitcoin, then I'd be trying to double spend, and everyone would be, no, I get the ledger. You don't have any Bitcoins. Mark has the Bitcoin, right? And since that ledger is distributed all over the place, right? Everyone has a copy. Now, so one of the things to think about is how do we know we all have the right copy? That's one thing that we have to coordinate, because we got to make sure everyone has the same copy of this ledger and they have a sort of universal truth. Why is this so interesting? Because if someone wanted to change the ledger, how difficult would that be? They would have to literally go into every one of your computers, if you're a node or you're supporting that network, and change it there, right? This is very different than if the ledger sat in the middle, right, in a honeypot in a centralized location, right? If the ledger was sitting in the middle, then all you have to do is go inside, hack that one ledger. Maybe I hack it, right? There's probably a lot of firewalls around that, and then I move the Bitcoin back to myself, right? So that's like, that's what a lot of people try to do whenever there's a lot of data centralized, right? But this is decentralized, yes.
So how often might copy of that ledger get updated?
Absolutely.
So
So
how
now
long do you take?
suppose Mark, transfers that Bitcoin to Dove, right? Now all our ledgers have to be updated, right?
Yeah.
So now we need a way in order to confirm that that's a correct transaction. First, you're going to check out who owns that Bitcoin. So you're going to look at the ledger and you say, okay, Mark owns that Bitcoin because that's who gives to Mark, and then Mark gave that to Dove. But what if I went in there and tried to take Mark's Bitcoin and give it to Doug, or give it to somebody else, right? So we have to stop me, right? So the only person who can initiate that transaction would be Mark, right? So we have to take into account how that works into the system, right? And so we're going to sort of discuss that. But the other question is, you know, obviously, you know, if I have a slow computer and I'm running the network, and you guys have fast computers, then there's going to be some legacy issues and so forth. So how does it account for these things, right? Which is actually very interesting. So the ledger operates completely open, and it operates in an untrustworthy environment. There could be people on the network who are sort of trying to do different bad things, right? Trying to manipulate through almost this Bitcoin, right? So it has to be able to account for that. So what are some major facts about this software? Well, number one, the software will be purely distributed, so a peer-to-peer system, composed of its users' computational resources. So we're going to allow this network to take over some of our computer resources. Right? Number two, the peer-to-peer system leverages the internet as a network for connecting the individual nodes. So without the internet, how do we connect these computers? We can't, right? So the internet is very important. It's providing the backbone to connect these nodes. The number of nodes and their trustworthiness and their reliability are all unknown. So remember, this is an open, anyone can join, right? So if someone just wakes up one day and says, hey, I want to join the network, we're going to allow that person to join.
You know what, maybe number three, maybe that's the reason why manufacturing isn't as much, is because all of the nodes are relatively known within the scope of the four walls of the factory, right?
Yeah.
And you don't have these unknown, potentially untrustworthy players. You know, it's not like you need someone to VPN from,
Exactly.
from some other part of the country in to, do a shift. You know, it's like everything that you need is contained within the four walls.
Exactly.
Right.
That's a very good point. So, we've seen a lot of blockchains, and one thing that fails for a lot of the blockchains is this whole permissionless, right?
Yeah.
People want to use blockchain, but they want a permission blockchain. So only, banks can be on it, or only central banks can be on it, or only, companies in the supply chain can be on it, right? They don't want to share it. They don't want everyone to come in there. So a lot of times people talk about blockchains, and they're talking about a permission blockchain, right? Especially corporations and manufacturing, right? Because then a manufacturing company is not going to let anyone jump on their network, right? It doesn't make sense, right?
Right.
So that may be one of the.
I mean, at least with the way the book lays out that public-private key, cryptography method in the digital signatures, it doesn't matter. I mean, you can still have, a trustworthy network even if you don't even know who's participating into it.
Yeah, that's true. But I mean, a lot of corporations kind of, view their data as proprietary, and that's their secret and so on, right? So they don't want, even if it may be sort of protected with public-private keys, encryption and so forth,
Right.
they just don't feel comfortable with that, right?
Right.
So I mean, if you went to, what's a good manufacturing company? I don't know.
Toyota?
Toyota, for example, say, hey, Toyota, put everything on your blockchain, and they get open. I mean, the executives in the board are like, no. We have a lot of competitors that want to sort of try to, understand our data. So that wouldn't be a very good strategy that you could sell internally also to the board, right? Supposedly you're the CEO of Toyota, and you say, let's do the blockchain, right? And you say, let's do the permissionless
Well,
blockchain.
it still has to depend on the application domain, right? I mean, maybe not for running their manufacturing, but if they ever adopted, like a direct-to-consumer sales model like Tesla, maybe that, payment system that they, do through that could be, valuable.
But that
wouldn't
sort of
be
gets back into the financial,
That'd be up-
even
yeah.
though,
The other area.
Yeah,
the
different
dot.
application domain, right? Yeah.
So, I mean, what's interesting about business organizations in all different facets, right, becomes, lend itself for blockchain implementation, whereas others won't, right?
Right.
So, I think that's what people are struggling with now, right? What part of their business can they use a blockchain? And the motivation a lot of times is, why do you talk to consultants and why do you pay thousands of dollars per hour to talk to consultants? Because the consultants are talking to all your competitors, right? And you're a Toyota CEO, and maybe McKinsey knows that Ford is using the blockchain in production, and you want to know how are they doing it, right? And so you're sort of getting some intel on how people are using this and what are the best practices to use blockchains. At this point, it's all open. There's no real on the business side, right? There's no real clear use case that this is great. All right. The peer-to-peer system's goal is to manage the ownership of digital goods, but this is also physical goods, as we'll see a little bit later, the digital goods. And And so ownership is a very, very important component of what's happening here. So this is the overview, the preview. This is a little bit of a complicated slide, but basically we're going to go through 7 different tasks, and these are all the tasks that the blockchain is going to try to sort of capture and solve, okay? So what's the first task? Well, it has to describe ownership, right? And what does that mean? Remember our example with Mark, there's 1 Bitcoin in the system, right? We need a complete history of transactions, right? Now, when you look at your bank account, what do you see? If I just, like, you know, made everyone build a bank account, I see $100 in your bank account, right? I don't know where that $100 came from, unless I look at all your transactions, right? Maybe your, you know, grandparents did it, maybe you stole it, right? But just seeing a snapshot of your bank account, I don't know. But if I know all your debits and credits and all this other stuff, all the transactions in your bank account, I'll know, you know, how you got there. So in the for Bitcoin, the blockchain is the transaction, the full history of the transaction. So that transaction, you'll see I have it Bitcoins first. Maybe I mined it. Maybe I sold it. Maybe I got it from Satoshi, right? And then I transfer that to Mark, right? That was another transaction stored, and Mark transferred that to Doug, right? So we'll have the full history, and we'll see where that transaction went. Okay, so we want to see to describe ownership, protecting ownership. So once again, if I'm owning the Bitcoins, you know, Mark can't hack into my system and give him stuff the Bitcoins, right? So we have to protect, you know, who the assets through identifying who the owner is, authenticating this owner, that's the person who can actually move the Bitcoin or transfer the Bitcoin. And then we restrict the rights of that property to the particular owner, so nobody else can come in there and move it, right? Also, storing transaction data, the blockchain data structure. Remember in the last class we talked about the blockchain data structure, the blockchain algorithms, the whole system of blockchains, the one application of this whole blockchain. This is where there's can be some confusion when people are talking to each other, right? Some people may say blockchains, they're talking about the data structure. Another person may be talking about blockchains and they're talking about Bitcoins, right? So we have to, when you have conversations about blockchains, you try to understand exactly what they're talking about. They're talking about the algorithms, they're talking about data, or ledger, or they're talking about a use case of it, right? So storing transaction data, the blockchain data structure is the digital equivalent of a ledger, stores the complete history of these transactions. So as long as everyone has a copy of this complete history, and one of the nodes goes down, whatever, you know, somebody hacks your country and knocks out the grid, right? All your computers go down, nobody can work for you. But don't worry, I mean, the blockchain is held up at least for Bitcoins across the world, right? So now when North Korea, you know, electricity goes back on, they can go in there and get full copies of the ledger and be able to do more transactions, right? Okay. What about preparing ledgers to be distributed? Now, here's where it's actually very interesting because you're providing this ledger and you're allowing for this transaction. You're barring double spend. You're making everything work. But it's potentially a very untrustworthy environment. So you don't have to screen any participants on here. So this is very interesting, right? And we'll see a little bit later that as long as there's 51% of people who are sort of good people doing good things, right? It's okay, it's going to work. To date now, no one hacked the Bitcoin blockchain, right? So it's been working pretty good, which means that, you know, the majority of people out there doing the Bitcoin transaction.
Or at least that we know about, right?
That we know about, right? Now, there used to be a case where a lot of the mining was sort of focused on a particular mine in China. And so the community said, well, this is dangerous, there's too much power going over there. People don't go mine over there. And the community pulled away. Because they all knew if 51% was owned by one particular organization, they could change the blockchain. So they actively policed themselves and told everybody, don't go, if you're going to go mine Bitcoins, don't go there, they're getting too much power, right? So I thought that was kind of interesting. Okay, so the blockchain data structure is unchangeable after any new transactions have been added. It is append only, so this thing is growing. How many blocks are in the blockchain do you think now?
Could be trillions, right?
Not trillion, about half a million. We'll actually, how many blocks? This is a little bit of a trick question because there are a lot of transactions within one block. We'll see how that is done. It's actually very interesting. That's called a Merkle tree that we'll learn about. This is definitely not something you've seen on the Wall Street Journal or you've really been exposed to probably never in your life. But, you know, raise your hand if you've been exposed with it. Unless you're really sort of into computer science, you won't be exposed. I never heard of Merkle tree. I'm a finance guy. So anyhow, it's an append only, therefore we're gonna prevent tampering. Now, as I mentioned earlier, the Bitcoin blockchain is publicly available. So every one of us can actually see it. We can see everything. So we're gonna, at the end of the class, at the very end, we're gonna look at the first Genesis block, right? And then we'll see how many there are. Right now, there's about, I think it's about 500,000 or somewhere around there blocks. Inside each of the blocks, you'll see there are a lot of transactions, but it's actually a summary of transactions.
So if you summed all those blocks together, would that be the market cap of Bitcoin? Is that what you're
It would tell you
describing?
the volume of blocks traded,
Okay.
but not exactly, because in each of the blocks, there's actually a summary of the transaction.
Okay.
There's no-
So you're just talking strictly the organ of record for the transaction data.
These are actual blocks, and we'll talk exactly what that means and what's inside a block. You'll actually see it, right? And we'll see how much was in the first transaction, when did it occur, because it has a timestamp, who did it go from whom to whom. The first person who started was supposed to be Satoshi, and nobody really wants who that person is, or a group of people. And that Satoshi sent 50 Bitcoins to Hal Finney, and that was the first transaction. And Hal Finney, unfortunately, he's passed away. But, that was the first transaction. Some people say, Hal Finney was Satoshi, and he was just trying to trick everyone so that, Satoshi has a lot of things, right? So there's many different reasons.
If I mine a new Bitcoin, should I have the Genesis block of Satoshi?
You will have the data of the whole blockchain of the ledger. Satoshi will be in there, right? But you won't have his Bitcoins, right? If you mine a block and you solve this, we're jumping ahead, you get a little bit of the Coinbase, you get a little bit of benefit, right? And we'll show you exactly how you quote mine, win, get new Bitcoins doing this, right?
Mm-hmm.
Okay. And it gets pretty interesting. Distributing the nodes interact to exchange information and update the ledger. So basically, we have to have a way that nodes talk to each other, right? And then also we have to have a way that all the nodes in the networks agree that this was a good transaction. Okay? Adding new transactions to the ledger, only valid authorized transactions can be added to the ledger. All members are allowed to add new transactions and supervise others. There was actually a really good comment, I think, last class. Basically, the network is policing itself, right? We don't have a centralized place that is sort of, confirming these transactions. Everybody in the network new transactions can join the network, but also polices itself, right? Because we're checking if that's a legitimate transaction.
Whenever you append, so step 4, whenever you append a new transaction to the end, is that process validating all prior transactions and then append? You know what I mean? Well, it's not just append, it's validate that the structure is valid first and then append to the end. Is it like that?
Right. So
Okay.
with 500,000 blocks, how can you quickly tell that everybody has the same blockchain? And there's a way to do that, and it's actually a very fascinating way to do that. And we'll learn about it. It's called a linked list. Now we're skipping all the way to the end of this lecture. Basically, you can one 64 character number. As long as we all have the same, then we know that your blockchain is the same as my blockchain, and add it on there.
And that's because the hash value of that has to be, I guess, unique and
Yeah, exactly. So we have all the same hash values.
right.
Yeah, so we'll see exactly how this works. If that's a little bit, vague, it's okay. This is we're going to clear this up throughout this lecture. All right. Deciding on the truth, and this is one of the, I think, most fascinating aspects of the blockchain. Remember, we can let anybody here, so there could be a lot of untrusted folks in here. But then we're going to arrive at a consensus on what is the truth. And how do we arrive on that consensus, right? And I think that's really interesting how this is done. Remember, if you're a computer and you know that you want to be part of the network, you got to play by the rules. And one of the rules is we got to determine what the truth is. And the truth is determined by whichever series is the longest series of blocks, right? So we all know which one is the longest. And we're all going to, one part of the rules is you want to join the network, okay, fine, you play by these rules. Okay? The actual blockchain is the one that's the longest. We're going to append only to that one, or the one that took the most computational power to build. Okay? And so that's one of the things for consensus. Consensus is fascinating. I think one of the intellectually, fascinating things that Bitcoin to blockchain contributed. Because consensus, it's not like all of a sudden we all agree. There's a high probability that this is going to be the next block. And then once you start adding more blocks on top of it, right, it starts pushing it down further and further. And now the probability is, as you have more blocks on top, won't change. It's very, very, high. It won't change. It goes to 99% and so forth. After so many blocks on top of it, it pretty much is in there forever. Okay. And so when we get there, I think you'll hopefully think it's kind of an interesting concept. So that's chapter 8. This is just the overview. We're going to go into each one of these in the next chapters. Basically, we're going to literally unravel each one of these and talk about each one of these things to have a better understanding. So I think chapter 8 it's a little bit a lot to digest. Just remember where we're going to go here. All right. Here's some sample questions. What are the 3 major elements of protecting ownership? First, you have to identify the owners. Second, you have to authenticate the owners because you have the right to do something right, and you have to restrict other people from doing anything for that particular property, right? So I'm the owner of this Bitcoin, and I'm authenticated. I have the right to copyright to move this Bitcoin to Mark, right? And so once I give it to him, then he's the rightful owner of that Bitcoin and owns to move that Bitcoin to somebody else, right? Okay. How a ledger is designed and untrustworthy environment. Basically, the ledger is unchangeable, right? So you can't tamper with the ledger. The only thing you can do is add to it, right? And that's it. Okay. What is a purely distributed peer-to-peer system composed of? Remember, these are the nodes. So you're allowing this network to use your computational resources of your computer. That's basically what you're doing here, going on there. All right. So let's talk about documenting ownership. How do we know? Let's look at this nice little example here. Mr. Bolt, right? Another Jamaican runner is passing the baton, right, in a relay race to Mr. Bolt. And so how do we know that who owns that baton right there? So who owns the baton?
The team owns the baton.
Okay, the team owns the baton. But between these 2 participants,
The passer at this point, right?
it looks like the passer at this split second is kind of having it, right? But then he's going to pass it on, so, another couple of milliseconds, probably a little bit more than that, right? Then Mr. Bolt's going to have that baton. And then if that happens, then what happens? Whoever it was handed off to last owns the baton. So if you're passing the baton to a runner, whoever has that baton, it was handed off to that person last. So my Bitcoins, I handed off to Mark last, then he owns the Bitcoin, right? So that's the idea of ownership. So describing the transfer of ownership, what we want to know here is you want to document ownership. How does it get involved? Describing the transfer of ownership and maintaining the history of these transfers. So in this ledger, we are describing the history, right, of transactions. Right? This is not like a snapshot of your bank account. You're given the full history, and if you kind of think about it a little bit like if you remember your accounting, your balance sheet and income statements. Income statements are sort of the change in some of the values over time. And so if you have all the income statements, right, you have all the transfer or added money into an organization. So the history of transfers, that's what we care about. Mr. Bolt owns the baton because he was handed it last, right? So someone handed it to him. So that's how we're going to determine who owns what. A transaction is the act of transferring ownership from one owner to somebody else. The act of transferring ownership relies on data that describes the intended transfer. So, for example, bank transfer form-wise, if you request the bank to make a money transfer to somebody else, right, on behalf of customer to somebody else. So whenever you're transferring money in your Citibank or Bank of America, you're saying, go do this, and then the bank says, okay, I'm going to go execute this and transfer your dollars to somebody else, right? And then whoever you transfer that money to then is the rightful owner of those dollars, right? So that's ownership. here are the things, and we're going to actually see this inside the blockchain at the very end of class, okay? So the first thing, how do you describe the transfer of ownership? First, you have identifiers. So there's an identifier of the person who's going to transfer the Bitcoin to somebody else. There's going to be an identifier for someone else. But on the actual blockchain, or in Bitcoin's blockchain, it's not Professor Liu. Here's one Bitcoin to one. We are kind of hashed. So you see some hashed version. You just see a bunch of numbers, like, and you see an arrow, and it's a bunch of numbers for Mark, and that's representing us. That represents the transactions. So with the identifiers here, one is the account that hands off the ownership, that's me, and the other is the account one that's going to receive that Bitcoin, that's Mark, right? You see the amount of the goods. First transaction that I referred to is going to be 50 Bitcoins, okay? You also see the timestamp when this occurred, right? So you have to be able to timestamp. I gave Mark a Bitcoin, what time is it now? Sort of around 12 o'clock, and then Mark has the Bitcoins, and then, he gives it to Dov at 12:05, right? So there's a chronological order, so this timestamp is very important. If you didn't have this timestamp, then it gets confusing, right? So you need a timestamp here. Here, there's a fee that you pay, the current owner pays the system for executing the transactions. If you increase that fee, there's a higher probability that some of these miners want to sort of, put that transaction.
See, that's what's totally clear to me. I guess it'll become clear as we go forward, but the process of executing those transactions where you're appending, to the end of the existing blockchain, does that have to be purely sequential, purely in series? Can any of those happen in parallel at the same time? Because as I understand the blockchain, the integrity of it has to be maintained. So if you have two relay batons being handed off literally at the exact same second, rounded to whatever, 10 to the -7 or something, but still it from the system's perspective at the exact same moment, like how do you validate that they both happen in what order? Does it have to be purely sequential from that perspective then?
So it kind of works as follows. There's a lot of transactions going on, right? Everyone's doing transactions Bitcoin, right? And then we got a bunch of these transactions and we create this, whatever this thing called a Merkle tree out of it. It's just a summary of all the transactions. What I grab may be different than what you grab, right? Even though we say, let's just grab it in the next 10 minutes, right? Just because I may have a slower system, you may have a faster system, right? You may be in the U.S., I may be in Asia. You may be grabbing more transactions in the U.S. versus in Asia, right? Basically, by and large, will have a lot of the similar transactions, but it won't be exactly the same.
You know what? It's because, I guess, by the nature of it, each one of the units that are being transferred are unique. And because that unit is unique, it doesn't matter if there's another block somewhere else on the chain that's also being transferred. Each individual block can only be transferred once at any given time, right?
So let's decompose it this way. If each block contains one transaction,
right?
Okay, there could be a case where I try to start mining this one transaction as the blockchain, and you potentially are mining a different transaction because maybe two transactions came at the same time, right? And if your node faster and this one if I node, so there's two transactions. Now we're trying to put it into the blockchain. Suppose you're faster than me and you figure out the puzzle, so you add it. What happens to this transaction that I didn't add? It's not fulfilled. As far as everyone knows, blockchain only this transaction that you sort of mine, put in, is there. So this other transaction I'll try to stick in, right? This other transaction will not have been confirmed, right? Okay, but it actually gets a little bit more complicated than that because actually in your block you're going to have a group of transactions, a lot of transactions, right? And I'm going to have a group of transactions too. There's probably a lot of overlap in our groups, but they're not perfectly the same. But if you still beat me in terms of putting that block on the blockchain, right, versus then you'll get credit, and all the transactions that you did will have to be confirmed. So if there was any transactions that I had that were not yours, they will still be open, and then the next person who's grabbing the transactions will be still, available for everyone, right?
Do we get in later to what it means to confirm a transaction?
Yeah, you'll see exactly.
Okay.
Just to go back to the relay runners, isn't it? Timothy said that you can certainly have the two different teams, the Jamaican team doing a handoff and the American team doing a handoff at the exact same time. And there's no problem with that because it's different owners trying to, it's only a problem if it's the same owner trying to hand off sort of two batons. He wants to give his baton to both the American and the Jamaican team at the same time. It'd be a problem.
Yeah, so that double spend problem is absolutely what this blockchain is trying to solve. That's just fun, right? I can't double spend my Bitcoin just to work with somebody else.
You can't give your
There's only,
baton.
in this case, there's only one button.
Well, you can break it in half and give it to two people, in a blockchain. Yeah.
Is it if two people solve the same transaction and they try to put it on the node at the same time, the guy who sends it, a couple to his kids, a couple to his wife, he will have more chains and he will be more trustworthy than the guy who just sits on his hands for a couple of minutes.
So the mechanism for the truth is defined by which chain is growing faster. Okay, so suppose that you have, me and you, we add 2 blocks to the blockchain at the same time, boop, and then you have all your friends mining underneath yours, right? Now yours is going to be the truth, mine is going to be discarded, okay? And so that's how it sort of determines, that's the consensus out of how it's going to work, right? It could be the case that here's a block, the block that was going to add something to it. We both add our blocks at the same time. But then for some reason, more people add into your block, then yours becomes the truth, mine gets discarded, right? And so that continues the blockchain on that side. And that's how consensus is actually.
But a false block can't be added. Like, I can't say, I've handed off the baton in any block to anybody if I don't have the baton.
Absolutely not. You cannot add to the false blockchain. And we'll see exactly how that works, why you can't add to the block. Remember, everyone has a copy of the blockchain, right? How do we know we all have the same copy, right? First of all, we have to determine that. You can look at one hash value and we'll all know. But the whole history is exactly the right history. So that's one of the really interesting things. It's called a read the list that we'll go through. But that's one of the things that are joined. But it could be the case that 2 blocks are added, which is fine. The consensus is reached by whichever side of the chain has the longest block. Okay. All right. Okay. So let's go to so the blockchain stores these transactions chronologically, and we know onto this ledger that's immutable. It says append only, and order matters. And we also know that everybody has to have the same ledger, right? So there's some weird around what is true. The current owner of the asset is going to be determined by checking whom the asset was handed off to in the last position, right? So like literally, we could go through. Assume everyone has a copy of this ledger. You can like literally go through and you can tell who owns what, right? And so if somebody doesn't have any Bitcoin and they're trying to make a transaction, right? They're trying to send a Bitcoiner, right? Then they can't. We'll say, no, you don't have any Bitcoin. We'll look at the ledger. It's all public common knowledge what the ledger is, and we all agree that everyone has the right copy of the ledger. So, that's easy. We can stop people from spending something they don't have, right? So now we have the integrity in the history of transactions. So this is, I think, the heart of what Bitcoins and blockchains is trying to do. Is this is why we can trade. I don't need to know you, right? I just need to know if I have to trust the system. I have to trust that you're playing on the system. I have to trust there's 51 people or just 2 people in the system. Now I look at the ledger and I say, hey, I don't know you. You're from North Korea. Okay, fine. You're going to send me a Bitcoin. I don't trust you at all. But I trust that in the ledger you do have a Bitcoin, and I do trust that if I do this transaction with you, I'll get that Bitcoin from you. So I'm starting to trust the whole network. I don't have to trust the parties in there, right? And so that provides a lot of integrity. All right, there are 3 to ensure only valid transactions are added. We need 3 measures: formal correctness. So the transaction contains all the required data in the correct format. Who are the 2 accounts? What is the timestamp? How much is transferred? If there's any transaction fees, and how are you going to sort of do this? We do a few proof of work right now. Semantic correctness means what is the intention of this transaction? Number I'm intending to get more Bitcoin, right? And this is very important because semantic correctness means that I can't give Mark something I don't have. So I can't overdraft my account, right? So if I don't have any more Bitcoins because I already gave all my Bitcoins out, you guys are gonna catch me. You say, no, Professor, you can't give any good points out. You don't have any really good ledger, and you have nothing. You had a lot, but you spent it all on that Ferrari. Yeah, now you have nothing. All right, and then also this prevents the double spend, so you can't spend it twice. So now this is formal correctness, semantic correctness, and then also authorization. Only the current owner of the Bitcoin is authorized to move the Bitcoin somewhere else, right? That way nobody can go in there into my account, hack my account, and move it for me, right? And we'll see a little bit later, there's a way in order to know that, I own those Bitcoins, and it has to do with the public and private key I own. And we'll see that in the next class, but not right now. Okay, so that's chapter 9. The complete history of transactions. This is the audit trail, and this is really fascinating. This is actually really, really fascinating, because if you think about the implications of this, how many people are accountants? How many people have ever had to audit an organization? How many people got audited? Right? We know what an audit is, right? It's a pretty painful thing, right? You have to go through all the transactions and verify everything that you did and where all the money is, right? So theoretically, if all your transactions are on the blockchain, right, you don't need any more audits. Why is that?
Because the governing business rule of the blockchain is that all transactions have to be valid to begin with, right?
That's right. So basically, you say, hey, I don't believe that's in your account. I want to audit you. You're like, hey, don't worry. You already have the blockchain. Just check my account. It's all there, right? So now, what is the implication of that? Well, the government, Congress allocates money around, and literally it goes down to grant organizations, and goes down to, money goes all filtering all down to grantees, right? And remember, if there's any grant that's over, some grantee gets more than $750,000, it automatically, an audit goes and has to be done, right? How much money is spent on those audits? A lot of money. If all these transactions are on the blockchain, theoretically you didn't have to do those audits, right? And so you could add a level of savings in that particular sort of, part of the government, right? So that's something that's really interesting, I think. And this could go for literally anything. If corporations were doing everything on the blockchain, right? Would you have to have audits? Financial disclosures, 10K, 10Qs? You can just take that information off the blockchain. Now, will that make a lot of people unhappy? Of course. Right? Especially if you're an accountant or you're a tax lawyer or whatever it is, that's going to really make you unhappy because, literally, that's going to disrupt your whole livelihood, right? And so, this is the potential tension, and not only in government but also in corporations and other places, right? And so that's why people are so interested in this concept because truth can be laid out there. All right. So this is the summary of chapter 9. Chapter 8 and chapter 9 are not as interesting as the next two chapters, as I hope you will find. All right, so here's some questions. What features are required for transaction integrity, formal semantic correctness, and authorization? Why does order matter in a transaction? Basically, what this is that, you need to have money in account in order to send money out. You can't just send money out. How do blockchains describe transactions? We'll actually see exactly what this looks like, okay? So remember, there's two parties, the amount of goods, how much are you sending, what's the time stamp, taking fees, and how are you going to do this proof of execution. Now, this is the most exciting, the boringest part of this whole lecture. So you must pay a lot of attention. How many people have ever heard of hashing? It's not the stuff that you're smoking, right?
Or running and drinking. Have you ever heard of the hash run?
What is that?
It's
The Hash House Terrier?
it's a run group that drinks at their own.
Oh, good.
It's a drinking club with a running problem.
Oh, hard.
My brother-in-law is in it.
Okay. So, when you think of identification, think of a fingerprint. When you think of a hash value, think of a fingerprint. I think that's the best way to think about it, right? And, here's an example. This is the tally that how do we know this is italic? Well, we can just look at his fingerprint, right? Assuming that, we have his fingerprint, right? We can confirm that yes, indeed, this is italic, because this is unique enough to describe who this individual is, right? But a transaction can have a fingerprint, right? It can have a hash value. A movie can have a hash value. text could have a hash value, and you can hash anything. It doesn't have to be a human being, right? So, when I take a picture of you, when you complete this course, we're going to take that picture, we're going to hash your face and whatever it is, and we're going to convert it into whatever this hash value is. And it looks something like this. Okay, what is this? Can you interpret this? No, it's just a bunch of numbers, 0 to 9, and then A to F, right? But this hash value represents that data. This is the fingerprint of that data. Okay, so this is what you have to sort of think about. This hash value looks like gibberish, right? You can't, nobody's like, oh, I have an intuition, oh, I know that's the palette. Well, right, this is just it looks kind of random. But this uniquely identifies that particular data, right? With high probability, right? So this is a cryptographic hash value, and it's uniquely identifying whatever data is there. All right, now, suppose I just move the data, I just like put something inside that data, right? What's going to happen to this hash value?
Change.
Completely changes, right? So suppose that I say, okay, look, this is the blockchain distributed ledger. Everyone has a copy, okay? And this is the hash value of that ledger, right? We can just look at this. We can hash our own on our computer. We can hash it and say, wait, do I have the same thing as this? And then we can confirm, yes, I actually have the blockchain data, same data you have. I didn't have to send the data over to you. We didn't have to match each one of the values. We just sort of look at this. If there's anything wrong with my data, automatically my hashes will match your hashes, right? And so we can instantaneously determine, do we have the same stuff, right? Yes.
So when we talk about the data, is it like unique data or group of data or like
And as you'll see,
how big can be the data like compared to the hash that
this
you
is
are?
what's so fascinating about this hash. Okay, this hash, secured hashing algorithm, SHA-256, invented by our friends at the NSA. This is industrial grade cryptographic algorithms. And we'll actually play around with this, and you'll see that there's other hashing algorithms as well. This is always going to be 64 characters long. No matter what the data is, you can put a whole movie in there, you can put 3 words in there, you can put 5 words in there, you can put a picture in there, you can put pixels in there, you can put voice, you can put anything you want, any type of data. Okay? It's always going to SHA-256 apply to that data is always going to give you 64 characters.
That's just identification, not the payload itself. That's
Okay.
the key thing.
Right, identification. So this is what blockchain is using. All right. So what are the characteristics of the hash function? And this is actually very, very important. So hash functions are computer programs that transform any data, any type of data, like text data, video data, picture data, numbers, right? Anything you want, into an output of fixed length, 64 characters. Okay. And they have to have 5 characteristics that make it a good sort of hashing algorithm. Number 1, it's very quick. Okay, so you put any piece of, like, this could be gigabytes of data, boom, it has probably a hash value, right? You put the whole blockchain in, boom, we get a hash value very quick, right? Number 2, so speed is important. It has to be deterministic, and what does that mean? If we have the same data, and we use the SHA-256 algorithm, it should give us the same hash. Okay? It absolutely give us the same hash, so we can just check very quickly. Should or must. If you have the same input data, must you get must have the same output data? Must have that. Absolutely must have the same output data. If any smidgen of the data is different between what I have and you have, when you go to do SHA-256 on our data, it's going to completely, we'll have different hashes. It's very likely that we have different if the data is different. Absolutely different.
It's identical, period.
If the data is the same, the hash will be the same. If the data is different, it's going to be completely different. There's only a very small chance that it actually is right. For all this, there's a really, really small probability. Very, very, very small. It is almost like inconsequential.
And the compute power needed to reverse engineer that is immense.
Okay, so you just sort of went ahead. First of all, 2 pieces of data that's going in. If I have like some 1 digit is off, is going to complete it into something, it looks random. And so you can quickly tell that this is not the same data that was hashed, okay? So that's pseudo-random. It's a one-way function, meaning that, this is what Mark was talking about, given any hash value, you cannot tell me what that is, the data that made that hash value. You cannot tell me, right? So if I give you that hash value, could you have told me what generated that hash value? Absolutely not. That's a one-way function. It only goes one way. Is that clear? And so that's providing some of the security with the hash value, okay? Collision resistance is that if you see two same hash values, there's a very small probability two pieces of data that went in there will result in two same hash values. Very, very small probability.
Can you give one example of collaborating? What condition might be that it's resulting?
That could be right, like in face recognition where there's some grayscales you don't identify, and that, or matching that becomes the same. The hash values could be the same. There are so many combinations, so there is a possibility.
There is a possibility, but it's so minute that people are just sort of discard
Ignoring
it.
that.
They ignore it because it's so minute, right? But nothing in computer science and this kind of stuff is 100% guaranteed, right? There's always like 0.001% chance that something is wrong. Okay? But
Data could be different, but the hash value could be the same.
that's right. Data could be different, but the hash value could be the same. That's called a collision. So the chances of a collision is very collision resistant, meaning that chance is so small that we don't care about it. Okay, that's collision resistant. All right. So let's take a look here. We're going to go to this website. So if you have your computer out, go to this website. It's actually much more exciting if you can sort of interact. Go to this website. Take a second, and we're going to do this together. Okay. www.blockchainbasics/HTML. This is the interactive part of this course. Okay. It's blockchain-basics with an S.com.
So they'll blocked it. Yeah.
Oh, they blocked it?
Yeah.
I can see it.
No. So this is the if you guys get to it, stop it. Okay, we'll just do it.
Let me ask you to unblock it.
Yeah, you block it. You block it. Okay, fine. But it is blocked. It's fine. Pay attention here. It's fine. So let's try this. What input should we put in here?
Hello world.
Hello world. Right. And now I'm going to hit this calculate hash value. And here are 1, 2, 3, 4 different hash functions. Okay. When you look, this is the one that blockchain Bitcoin uses. But there's even more. You know, this is even longer. SHA-12. Right? This is SHA-1. This is NB.
I can't come out for somebody to call it.
Double employees?
This is the one that's most popular. Okay. Now watch what happens when I change this. Instead of hello world, right? I'm gonna, say hello world 1. I calculate the hash value. SHA-256. You can just look at the first couple of digits. Completely changed. Okay, completely changed. So one slight adjustment to the data completely changes this hash. Right? So that's one thing to observe. And how hard would it be if I just gave you this? I said, okay, what data generated this? Could you go back and tell me, oh, that was hello world, exclamation 1? Impossible, right? It's a one-way function. It only goes this way. You can't go back this other way, right?
Can NSA?
Huh?
Can NSA do it?
NSA can do everything. But there's only a few NSAs here in that caliber of computational sort of power that can do whatever they want, right? If they created the SHA, I'm sure they could unwind everything if they wanted to.
Google and some other groups worked together to prove that the SHA-1 was not secure, and they created a website about it, shattered.io, that has some really interesting infographics and a lot of like interesting information about this stuff.
What is it called?
It's shattered.io.
Okay. Please send that. Please send that. I definitely want to bring in. Yeah, everybody has to move to our SHA-1.
Yeah.
SHA-1, yeah.
So right now, the standard is SHA-256, and isn't SHA-1 used on almost all Wi-Fi?
It is currently, yes.
Is that right? No, my Wi-Fi is so, not interesting. Home Wi-Fi. What's that? Home Wi-Fi. Home Wi-Fi. Home Wi-Fi. Oh, interesting. Okay. All right.
So I have a question.
Yeah.
So we'll say Bitcoin is using SHA-256. That's the hash function, right?
Yeah.
So is it hard to switch to the 512?
No,
Okay.
it's not hard.
The algorithm.
It's just the, okay.
So basically, you call a different method or a different function,
Okay.
right? And some people say that Litecoin is using a faster, algorithm. I don't think they're using SHA-1. There are many other types of
Isn't that Lyra?
security hashing algorithms. These are not all of them. There is a whole field of cryptography that deals with that. Right? We're just scratching the surface. You can go really far down this rabbit hole. And I think
Is there a relative computational time between these algorithms? Like,
Yeah.
SHA-512 takes twice as long as 256? It's probably not exactly twice, but
It's probably not exactly twice, and depending on how big the data you put in here, right? As the size goes up, this might go a little faster. But I don't know the statistics. All of these are really fast, relatively fast. They're nanoseconds.
no, I understand, but
Let's get
like every algorithm, it has a component to it.
So now what we're gonna do, because, 64 characters are a little cumbersome to look at all the time, we're just gonna look at, I think about eight of these, okay? So we're not gonna do, we're not gonna write all of the 64 characters out every time we do this. So we're just gonna sort of concentrate on the first couple of them, okay? Just, without loss of generality, just so it makes the computation easier for the eyes. So you can put Professor Lou and hit the calculate SHA, you should get, 6 dB. And then if you put Professor Lou with an extra W, you'll get 0B03, completely different, right? Okay, fine. So
So I have a question. So it's only with this hash function, it looks like alphanumeric only, or
so it's
Hexadecimal.
0 to 9, and then A to F.
A to F?
Yeah, that's it.
Any hexadecimal. Hexadecimal.
Hexadecimal.
Hexadecimal.
It's a representation of
Hexadecimal,
the
that's what it is.
256 bits.
Yes.
Oh,
You could actually put that as a 256-bit string of zeros and ones.
Oh,
Yep.
okay. That's it. So you can only do numbers 0 to 9 and K to
Yeah.
Okay, now, blockchains must often hash many transactions data at once. We're going to learn 5 distinct hashing patterns for different situations, right? So, if you have your SHA-256 calculator, I want you to just put in hello, hash it. Also, you guys are helping me check the lecture notes if they're correct. Right? Just put hello by itself with no space and hash it. You should get 185. Those are the first 3 digits, F8DD3. If you then delete that and then you put world with an exclamation point, you should get 514. Okay? So this is independent hashing because you're independently hashing that data one at a time, right? Which is not very efficient, right? But this is one way you can do it. Convert every single word into a hash, independent hashing. Alternatively, you could hash the following, a hash of a hash. So stick in hello world, exclamation, you should get a hash. Then you copy this hash and you stick it back into the SHA-256, right? So a hash of a hash, then you should get this. Okay? So it's kind of like a composition function, right? And I believe like the addresses for your Bitcoin, the hash of a hash. Okay. This is called duplicate hashing. Number 3, you could
You have to reverse it.
how could you say that?
You could never reverse
You could
that.
never
I mean, you can reverse it, but wouldn't somebody have to know how to reverse it to get back to?
You would need to know that.
Because you did it twice, right? You hashed the hash.
Exactly. So I would have told you look, here's the data, I'll give you a copy of the data, and now say, okay, do the hash with the hash, or do the repeat with the hash. So you hash it once, and then I have to tell you, okay, only grab the first 8 digits and hash that, and then we can confirm, right? Why would we do that? I mean, we're extra paranoid or something, right? Because NSA is hunting us down or something. I don't know why you would do that hash with a hash, but you could do it. You can hash it again. You still get 64 characters. You can hash it many different times, right? Yeah, I mean, as long as we have this. If I have a private key, then if I'm using the private key, I'm using this hash. Then if I share the public key, then I should be able to decode that, and I can do that. And I think that's how it's going to be multi-factor authentication right now. That's how it's going to be. And technically, if you have those keys, you can. So, but normally you don't. So for people who are going to go buy some Bitcoin now, because now they know what the hashing function is, the only thing that you have to remember is don't give anyone your private key. Yeah, that's it. Yeah. You shouldn't really share your public key all over the place, because eventually, they can figure out who you are. If you put on, like some people put it on LinkedIn, give me some Bitcoin, they put their public key out there. But there's a graduate student who figured out that you could sort of check the whole internet for people's names and emails, and then now you have the public key. And if you left anywhere on the internet your private key, they can go grab this private key. What happens a lot of times with the hacks to the exchanges is somebody, the exchange, said, okay, you can trade on the exchange, but give me your public and private key, and we'll store it somewhere safe. But it wasn't safe enough. So what the hackers did is they got into the exchange. They didn't hack the blockchain, the Bitcoin blockchain. That was never hacked. They went in there and they stole all the public and private keys of these accounts. So basically, they took the money or the Bitcoins from these because they use the public and private keys of these accounts. Then you see in the news, Bitcoin hacked, right? But it was actually the exchange that was holding the public and private keys that got hacked. The Bitcoin blockchain never got hacked. Right? And then people say there's a lot of misinformation. Oh, Bitcoin is so dangerous. The blockchain's been hacked. You could look at the news article. But when you read it, it's actually the exchange that got hacked. Right? Okay. You can also put multiple pieces of data, and then the question is, how do you combine this data? You concatenate it. Can you put a space in it? Yes or no? Remember, if you don't put a space in it, it's different than if you put a space in, right? You can put a plus on it. So you can combine the data and we send it through once. This is sequential hashing. This is actually very, very interesting. First, what you do is you take hello and you hash it. Now you have another piece of data. Remember, this is time, so this happens first. Now you can take this value and another piece of data, and now you can put them together. Now you can hash that. Now, if I give you this, right? I said the first transaction we did a hello, and then I combined the hash, the first 8 characters, with the next piece of data or transaction, world, and when you see that, you should arrive at this. If you see that, then we have the same 2 data points, right? So this starts to build on what the blockchain is going to do. Okay, combining transactions with hashes, right? Now, the only thing I have to do is look at the very end here, right? All we have to do is check the final value. Remember, this could be really, really long, right? There's many, many things here, many blocks here. And now we're combining hashes and data, and that's the essence of the blockchain. Right? So that's why I said at the very end, at the beginning, we can just compare hashes and we'll know we have the same blockchains, right? So what I didn't tell you is, and we haven't figured this out yet, how does this become a transaction? Where's the timestamp, right? We're still missing many pieces here. But the essence is something like this. Here's data, get a hash, take that hash, combine it with the next block, and then hash it again. There's also something called hierarchical hashing, and this is going to sort of feed a Merkle tree. And the Merkle tree is going to be, these are going to be transactions. And basically, you take a bunch of transactions, you hash those out, and then you're going to combine the hashes. Okay? Maybe you put a space between them, maybe you put a mark between them, somehow you combine those hashes, and you hash that again. you could have many, many transactions here, right? And then we're percolating up to one tree. This summarizes everything. Now let's take this final value of the Merkle tree into the blockchain, and that's exactly what happens. Right? That's exactly what happens. So the Merkle tree is used to summarize a bunch of transactions to stick into the blockchain. So we're going to stick one hash value in the blockchain to represent all those transactions, which is interesting. Okay. So the summary of chapter 10, there are many different hashing functions. So we're going to talk about SHA-256, but you know that there are many. And some of them are not as secure as others. What happens when quantum computers come around? You get even longer hashes, right? But all this technology sort of falls apart. You'll see, right? So one of the dangers that the blockchain as it is right now is when it uses SHA-256, one of the dangers is quantum computers. That's going to change. So people are trying to create ways to be quantum computer protected from that innovation. But chances are we're going to see once quantum computer becomes mainstream, that the hashing algorithm is going to be more sophisticated. Okay. What else can we talk about? Remember, it's always a fixed length, 64 characters long, hexadecimal, and these are the 5 different types. Right? I'm sorry, these are we want these 5 different traits. So in a test, I'll probably give 5 traits in the hashing algorithm. And so that's, has to work really fast, so speed is important. Has to be deterministic, so we put the same data in, we get the same hash values. Right? Has to be pseudo-random, meaning that if I change my data a little bit, it's just going to look that the hash is going to be totally completely randomized change, right? It's only one way, so if I give you the hash value, you can't tell me what data I gave you, right? It's impossible, almost impossible. And it's collision resistant, meaning that if we have 2 pieces of data, it's very rare that that's going to result in the same hash. Okay? Very, very rare. So rare that we're not worried about it. Okay? All right. So let's talk about hashing in the real world. Now we're going to get even more into how this whole blockchain is going to work. So one of the things to think about, I think this is a really, really nice example. How many people have been out to like a concert, somewhere where they take your coat? It's probably a pretty fancy or, party when they take your coat, right? Most of the time, like, people just throw their coats on the bed, but once, you put the coat there, they give you a little ticket, right? This is like high end. So let's say you have a coat, and there's a ticket. They give you the ticket, right? And that ticket represents what? This hanger. This hanger is holding your coat, right? So you can think of your coat as data, right? And this ticket is telling you where the location of this data is, right? You can think about that as the following. Now, what happens, if you lost your ticket? Well, then they have to say, okay, come back here with your code. It's kind of painful, right? And what happens if you have too many drinks and you accidentally exchange your ticket with somebody else? When you come back, you're going to get the wrong code, right? Right? So there's this whole notion of the data and representing. Now, what would happen if we took this ticket and we went over here and we deposited this ticket inside this pocket of this code, right? And then we did that over and over and over again. What would we sort of accomplish? Well, we'd have some order, right? So when you get this code out, then you'd reach in the pocket and you pull out a ticket and you're like, hey, so then what's the next piece of data? Oh, it's over here, right? So you could start ordering these codes, right, over time. So what happened there? You took the reference and you put it inside with the data, right? And so this sort of notion of putting hashes inside with the data, or summary of the data, allows us to sort of organize this stuff in a particular order, right? Okay. So hash references are very, very interesting. And think of the cloakroom. This is where you have your coats and the tickets. So each of the ticket is pointing to a certain jacket. The hash reference points to a certain piece of data. So the ticket is the hash reference, and the jacket is the data. If that code in particular or hash reference changes, it means that the original jacket or data is different. So there's a sort of map between that particular ticket and the data. So if the jacket changes, data changes, the next reference is broken. Hash references protect blockchain users from retrieving data that have been changed in a malicious or technical error different way. So this hash reference is going to be very, very important, very key to sort of how the construction of the blockchain sort of is formulated. If the underlying data is modified, the hash reference becomes broken or invalid. So here's the thing. We can look at the final hash value. We sort of talked about this a little bit, of the totality of this blockchain. And we can see if something's wrong with the data that you have versus the data I have, the distributed ledger that you have versus what I have, the whole blockchain that you have versus what I have. So we'll know very quickly we're going to append to the right blockchain, right? Because of the final hash value. So let's just call R1 valid hash reference to this particular data. It points to the data. I bought 50 Bitcoins. If for some reason I change this and I say I bought 5 Bitcoins, what happens to this relationship? It's broken. Okay, it's broken, right? And so whenever it's broken, the original hash reference, this invalidates, then you know that this is something happened. Okay, so you can quickly tell if your data was altered. Here's an example. There's a different hash reference here. This is okay, because now I'm going to this data, which is the 55 Bitcoins, right? All right. Now, what does it mean to store data in a chain-sensitive manner? So, what is the point of sort of all these hash references? You want to, what?
Sorry, keep track of things.
Keep track of things, make sure that what you have is what I have. But there are many different ways you can do this. What you have is what I have, right? There's two methods in particular that we're going to talk about. There are two classic patterns for using hash references to store data in a chain-sensitive manner. So the idea here is if anything changes, you'll automatically know very quickly. So if any data changes, if anything, someone alters the data, then basically what's going to happen is we'll understand this. So the first method is the chain method. And if you understand this, you will be able to really, really understand the blockchain. Okay? Everything else is small little details. This is the essence of what the main, idea is. Okay, so this is not new. This is something that's been well known. It's called a linked list. Okay. So each data contains the hash references to another piece of data, and R3 is the head of the chain. So you can think of this as a hash value, and R3 represents this whole chain. Okay. And now the way it works is that you can think of this as one block. The first block in the chain is called the Genesis block. And the Genesis block has no reference to the prior block, because it's the starting Genesis, the beginning. And inside, it's holding data. Now, this data could be just, sold 5 Bitcoins. It could be a timestamp. It could be a Merkle root of summarized transaction. You can do whatever you want in there, right? So you have this block. R1 is the hash reference, or the hash for this data. Remember, the hash is 64 characters long, it's pseudo-random, right? Collision resistance, and all this other stuff. We're going to put this inside this next block. Why do we do that? Because if anything changes here, this is going to change, right? And that change is going to transfer all the way down to R3, right? So basically, you just by looking at R3, and if your R3 is not my R3, then I know something's changed, right? I don't know exactly where it is. We have to go digging deeper, but if I can quickly determine that something's changed, that's not really yes, but if you, okay, so suppose this is always SHA-256, right? Suppose this is always SHA-256, and so that's always SHA-256. In terms of hashing. Okay, So linked list is basically, this could happen at the beginning of the day. Now we have another transaction. We had, I bought 8 more Bitcoins. This is just data in this block, but this block also contains the hash value of the previous one, right? We can hash this too, right? No problem. And then you got R2. And if there's other data that come in, this could be a transaction, whatever it could be. You could hash this R2 with this all together, right? Then we got R3. And so what's interesting about this is you are combining actual data with hash value. Right? But a hash value is basically data, 64 characters, it's sort of typical things to remember, right? Do you have any questions? This is very, this is the crux of it all. This is if you can sort of get your head around this, everything else is going to be like, okay. So we'll stay here for a little moment, and we'll just enjoy the way. Yeah.
Question. So is this where the whole entire ideology in blockchain, where they say that nothing is deleted, it's just added on to the chain? Is this where it comes from?
Yeah. Okay. So remember, why are we doing this in the first place? Because we want to know that our blockchains are the same. Right, looking at one value. And so it's the case that the integrity of this blockchain, in a linked list, it can be summarized in one value. And any changes here or here or here will affect the whole chain. Well, they'll affect from here on the whole chain.
In computer science itself, linked list is pointing to the previous and the next node. And those pointers are within the block itself. That linked list, that has that value also. So that's part of the value. That's why you can hash the hash value and the value. I think that's how we get it. This is the typical way how linked list works. So linked list is a concept that computer scientists have known forever. Forever. This is not new. So using linked lists in a peer-to-peer network. So you're grabbing two things that are not new, peer-to-peer has been around, and linked lists have been around. You're using them in conjunction with each other in order to solve the goals. That's all. And that is the innovation, right? So, the innovation of Satoshi, or whoever this person is, or a group of people, is not coming up with something new. It's actually combining two old things together to come up with something really interesting. Okay? So there's a whole history of linked lists. And you could go and, probably take, it could be a lot of pages on linked lists, and probably be, just any picture of peer-to-peer. But linked list is probably older, right? Yes.
Much older. So this is our class of computer science.
Yeah.
Really? But linked lists are mutable, intentionally mutable.
Mutable,
you
yes.
can put things into the list.
So that you can change
out
it.
of the list, and you change the pointers. But here,
You hash it, and that's why.
The hash would have to change to change the pointers. So linked lists are, but putting hashes in the linked list, putting hashes in the linked list makes it immutable.
That's what it
Because
happens.
my previous link, if I wanted to put a transaction into,
In
between A and B,
I cannot do that.
okay, I'd have to put on, and this is new transaction D.
Yeah.
I have to put R1 in D.
Yeah.
It's a point there, and then I'd have to have a new R1 prime. And I have to put that into B. So I'm glad you got that, so you can explain something to me, right? Yeah. If this is a pointer, it's just pointing to the data location, right? Well, in a linked list, it's pointing to a data location. Here, it's pointing to a hash summary of a block. Exactly. So, so the pointer is So this is actually pointing to the hash summary. Yes.
In this concept.
In this concept, it points to the hash result of that block. That block can be stored anywhere.
It doesn't matter.
When it's a linked list in memory, it's more like the code hanger. This is on hanger 3. Go to hanger 3, get the code. Oh, that code has a ticket that says this is on hanger 27. Pointer, that's a little bit, that's not correct. That is not correct in this case.
Yes,
It's just
this is
a
the
hash
hash value.
result. They said it's a pointer.
That's how it becomes immutable.
Yeah.
So
But
because
this is the hash result pointing to that block. And presumably, only that block, even if you had 500,000 blocks or 500 million blocks,
that R1 will only point to one of those blocks.
Perfect. So this is the immutability. And the immutability comes with the hash values. And the combination of the hash value and the data.
Quasi-unique hash values, just the way, a table sequence in Oracle is unique values, they happen to be in sequence.
Yeah.
Because Oracle keeps the sequence.
So I think,
These are a way to independently keep immutable sequences.
so when you say that blockchain is an innovation that combines other technologies, it's not just the link list peer-to-peer, but it's the cryptography as well.
And hash value. So when you learn linked list, this is just a pointer, it's not a hash.
The concept is the same concept, but they use the hashing to derive the next block and the previous block.
So linked list is actually, this is actually just pointer.
Yeah.
So they put the hash value here, that's another innovation, right? So it's a linked list with the hash value here and the peer-to-peer.
Yes, linked list is the concept they use,
Yeah.
but the hash value, putting it over there in the block, makes it,
Makes it,
that makes it immutable, so that
that
I
makes
cannot.
the previous block immutable.
So,
Because
do you think
it's
this is a real innovation? It is a
it-
major innovation from a computer science point of view.
The major innovation is the hash makes the previous block immutable. Meaning if you change the previous block
Yeah.
and you have a pointer to the previous block
Yeah.
and you compute and the previous block no longer has
Has
this
the same-
hash,
Yeah.
you know somebody has changed that block.
Okay. Interesting.
And that's why you only need to know, like you're saying earlier, the hash
Only
of the
the hash
last
value.
block, the final
That's-
block, right?
That's where I can hide it. That's all.
So unlike the hanger, which says, oh, if you find hanger 3,
Yeah.
hanger 3 is where hanger 3 is,
Yeah.
you can't tell if someone changed it, you can't tell if someone put somebody else's coat on hanger 3.
Yeah.
This, so let's say I give you my coat, and you
Yeah.
give me the ticket to hangar 3,
Yeah.
but you actually put my coat on hangar 2.
Yeah.
When I come back, I will get somebody else's coat.
Yeah, yeah.
And this one,
won't.
you're guaranteed, you
You can only get that.
can only get that coat.
Okay. Okay, so linked list is something that we never teach in finance. Hashing is we never teach in finance. And never in my whole life have I heard of a Merkle group.
That's still new.
And you survived just fine.
I'm still alive. A Merkle tree. So this is a Merkle tree that I learned, you know, I'm almost 50. I have my life. I finally learned something new. Good. So if you never heard of a Merkle tree, don't worry about it. It's fine. When I teach you the MBA, it doesn't even know that. A Merkle tree, I don't know. Nobody teaches this business law. What do you want, computer science? Yeah. Basically, like the first thing around. Okay, so anyhow, a Merkle tree is a summary. So here's all your transactions. So sold Bitcoin, sold 8, sold 1. And so basically what happens is you get the hash value, you put them together, and then you take the hash of this combined, and then you get R1, 2, and then you take, again, these hashes, and you combine them, you get R3, 4, and then you take these two hashes. Remember the hashes are super, and then you get to the top of the Merkle tree. Now, if you store this Merkle tree inside your block, you save a lot of space, right? Is that what people use in computer science? Yeah. Okay.
Mhm.
So basically, what we can do is probably take any certificate and put as much information as you want, and we're going to Merkle tree it all up to one hash, and just stick that one hash into the, Grand Solutions University blockchain, right? That will summarize it. And then where does all this data get stored? In a database? Wherever you want.
Anywhere you want.
And this gets stored next to it, so you know. Perfect. So the Merkle tree is going to be the summary of all the transactions in each of the blocks of the blockchain. So you're going to say, who owned it, who are you giving it to, how many timestamp, and give me a summary of all the transactions, which is going to be this, right, the hash value of the Merkle tree, right? So at least for business students, this is all new. Computer science people, this is trivial. This is what's so fascinating about blockchain too. If you're a computer science person, you understand all the technical details, but you don't know how to use it. Well, why people will pay for it, right? The business people can figure out why people will pay for it, but they don't know how to do all the technical details, right? So you actually need two people in order to make this successful. If you just get a bunch of computer science people and give them a lot of money and say, okay, go do something with blockchain, they can't solve the business problem. But if you get a bunch of MBAs together and say, okay, use the blockchain to create a business, they don't know what to do, right? They're like, I don't understand Merkle tree. I've never heard of that, right? I don't know what hashing is, right? So you
And our
need a
technical
combination.
people like to keep it that way.
So you need a combination that makes this work. And maybe one of the reasons why, we haven't seen the real innovation is that we haven't seen enough collaboration between the two groups, right? Maybe, we'll see. I think Grant Solutions has a ridiculous advantage because you have the data, you have access to the whole process, you understand this whole supply chain. Clearly, you have business people and the technology people all under sort of the same roof, which is actually, I think it's explosive, it's very interesting. Okay, so, let's talk a little bit about this hash puzzle or proof of work. Anybody do any Bitcoin mining in this room besides Mark? Okay, mining, what are you mining? Ethereum?
Well, it's whatever pays the most at the moment.
Oh, that's good.
Yeah.
So, one of our interns, his name's Josh, he set up a mining rig for me. We have 5 GPUs running, right? Costs about $3,000. We set it up. We mine about one half Ethereum per month. So Ethereum is trading at $400. We make $200 covering electricity, sitting in the parents' basement. They're not too happy, but in the wintertime it warms their house. So they're happy. In the summertime, we didn't expect it. It heats up the house, so the electricity, there's air conditioning. So far, we're kind of just breaking even. It's much more interesting when Ethereum's at 1,000 than it is now. Right? A lot of sort of they're mining in the dark. Yeah, I was thinking about doing some mining in my office just for research purposes. But yeah, students mine all the time, right? So it's fascinating. Okay, anyhow, so what is mining, this whole concept of proof of work? It's actually pretty interesting. Basically, let's start out with the analogy here. Suppose that you didn't know the combination for a particular lock. How would you figure out how to pick this lock? How do you open this lock? What would you do? You start 0, 0, 0, go 1, 2, and just keep going, right? Is there a more elegant way to do this?
Yeah. I mean, educated guesses.
You
could.
Well,
if it's for someone, you could say maybe it's their birthday, or maybe it's their significant.
Yes, right. But suppose you don't have no idea who this person is. What the block is.
Yeah.
Suppose this block is well built, so you can't sort of start at the bottom and just move. Yeah, then you just have to use brute force, right? And so this is kind of interesting. So a hash puzzle is set up so that the only way you can solve it is brute force. And
6,000 possibilities, right?
yeah, four. 9 All right. So basically, what you can do is this is how a hash puzzle is set up. You must just do the work. So the hash puzzle has 2 components. So one is the data that's going to be unchanging, right? And the second component is this thing called a nonce. Nonce is another term that I never really encountered in my whole life until now. And nonce is something that actually changes, you can change this nonce. Basically what you're going to do with this nonce, and the only way that you actually ever really figure this out is if you do it sort of once. So, we're going to go back, and we're going to go painfully do this once. Basically what you do is, you have hello world here, and you have a space, you're going to do 1. Now you're going to put 1 here. And you're going to push calculate the hash value, and we're going to have a little contest. And basically what you want to do with this 5, 2, 3, 6, you want 0, 0, 0. Now the more zeros I tell you to do, the harder this becomes. And now this becomes literally you just have to brute force this. So instead of 1, you try 2, 3, 4, 5. You keep going up and up and up and up until you can solve it these zeros. You can make this puzzle really hard if you say, oh, I need the first 6 zeros. Because just by luck, you're going to find this thing. Yeah.
Okay, so hello world, in this example, hello world is our data, and then we decided to use space to separate them, and
that's
nonce is whatever you put after the space.
That's right.
Okay.
That's right. That's exactly right. And so suppose that we said, okay, whoever gets the first 6 zeros here wins the competition. And for winning the competition, you get to add the next block of the blockchain. In addition to that, we're going to give you 12 Bitcoin.
to do it? Okay.
As 1,000,
If I
whatever,
said,
5,000.
we are going to give you 0.000000125 Bitcoins, go. You'd be like, I don't want to do that. That's not worth my time. So what's really interesting, Bitcoins is set up so that it incentivizes the network to spend time to do this game, right? If Bitcoins didn't overcome the costs, and what are the costs? There's a fixed cost. There's basically electricity and just setting up your hardware, right? That's it. That's the cost. Yeah. You can get a high school students program in for you. It's not complicated. Those are the two components of the cost. So what do people do? They go to the coldest place in the world with the cheapest electricity, and they mine, right? They'll keep mining as long as it's profitable. So Bitcoin set up the economic incentives. Well, they did a good job. Did they get lucky? Maybe. Right? Did they think that Bitcoin was going to trade for $8,000 or almost $19,000, $20,000? They didn't expect that, right? But they got the economics right. The economics are such that right now it's still profitable to mine, so people are doing this. What's going to happen when all the Bitcoins are mined? The 21 million Bitcoins are mined? We don't know. Will they still be incentivized to run these things with the transaction cost that they get? Maybe, maybe not. We don't know, right? So after so many Bitcoins are mined, basically what happens is that the amount that they pay you keeps getting halved, right? And so, at some point, it may not be economically sort of interesting to mine Bitcoin, right? But right now, it's still kind of interesting. There's a
trading. Then comes trading of Bitcoins, right?
Could do trading with Bitcoins, right? So right now, there's a in the community, since we're solving these puzzles and we're using electricity, we're kind of right now we're kind of like in the green mode. If you want to save the world, and just running your computer and using electricity, some people have an issue with that, right? And so instead of doing the proof of work, which is exactly this, basically finding the nonce, so you get a bunch of zeros, you do this competition, so you get some Bitcoin based on Bitcoin, you make some money. And once you put the blockchain on, right, you add the blockchain, you are adding another block to the blockchain. And as the more and more blocks added in the blockchain, the higher probability that this is preserved forever. Right? And so you're helping the whole system go through because you're incentivized. You're economically incentivized to do this, which is fascinating. So now you have a group of people to figure out an algorithm that works to incentivize the other people to buy their computer to do this. Right? And so that's another really interesting component of it. And I think that's also kind of missed. If they set the amount of payment out for mining wrong, incorrectly, nobody would have done it. Yeah, I don't want to do that. That's a waste of time. So, when you are thinking of your business, when you're going to do some kind of business blockchain, you must incentivize the participants, right? And this is where academics do a bad job. This is where practitioners do a great job. Academics are always incentivized as something curious and interesting and sort of intellectually stimulating. Unfortunately, right? We just like to do that all day long. So you need a practitioner in order to understand what are the motives. Why would someone do this? What is the advantage? Isn't that the biggest difference between all of these e-currencies is the incentive to do it? Like, ultimately, it's all paper property, but Bitcoin Cash and Ethereum just has a different incentive to mine. Yes. I mean, some cryptocurrencies are set up so that the incentive is use it because it's hard to track, like eCash, whatever, Zcash, Monero, and so forth, right? Others are sort of incentivized to save the world. And I haven't seen any of that really take off yet, right? It's always, there's always some kind of motivation why someone would use this. And that's important. I think that's like one of the key things that when you create your business and you pitch. Try to think, why would someone do this? Why would they use this, right? Why would they use this blockchain? What do they gain from it? So, constantly ask yourself, would I do it? Is it interesting enough to me that I would actually interact with this blockchain? I think that's very important. Okay, so that's the nonce, that's the proof of work, behind zeros, and that's a good analysis. Okay.
difficulty level, as you saw, is you set the output of the SHA value to the hash value to be 0000. The more zeros you add, the harder it's going to be. The hash puzzle, as of now, is called proof of work. But people are starting to think about that's not very fair. Let's do proof of stake. So what is proof of stake? Proof of work is always a hash problem in the computer world. Trying to figure out the SHA value of a bunch of zeros, right? That's like literally, it's like a lottery. Because you don't know who really is going to win. Right? But what is proof of work? I mean, proof of stake. Proof of stake. This is another term that people are talking about. S-P-A-K-E, proof of stake. So it's bad for the environment to have our computers running like that. I think, the amount of energy used to be mining Bitcoins is, I don't know, power a small country for a little bit. It's a waste of a lot of electricity. That's what people are saying. So proof of stake, what is that?
It just seems like a pyramid scheme to me. It's like,
So the guys who do proof of stake said, okay, proof of work is bad for the environment, let's save the world, right? You can't just ask people using electricity and computers to be doing that. So they say, let's do this. Here, you stake a lot of coins, okay? And suppose it's 10,000, units of this particular coin. And you just hold that, and you leave your computer on our network, okay? Now, you're sort of this node, you're like this master node. And as long as you agree to keep our network up, remember, basically, in order to keep the network up, you need nodes, right? To sort of, figure out these transactions. When these transactions, we'll give you some percentage of this transaction. So that's the whole sort of thing that people are trying to think of. Ethereum is supposed to move from proof of work to proof of stake, because Vitalik doesn't like hurting the environment. It's, a young man who's, trying to save the world. So what people are trying to do right now is they're thinking about how do you not run your computer so much? How do you use electricity? Just keep your computer on there, not have to do the proof of work crazy puzzle, right? Hashing puzzle, and that way sustain the network, and also sort of reduce the burden on the environment. So that's what people are thinking about.
but doesn't that also mean that the people who are like the first stakers are the ones who reap the largest reward, and then kind of like subsequently every staker after them gets less and less and less, like exponentially less?
This is what people in the crypto community say. That's unfair, because the rich people are going to get rich. Yeah. And that's not right. I mean, right, you need like 10,000 of these whatever currencies, whether it's Ethereum or Monero or whatever, in order to have one of these super nodes. Only rich people can do that, right? Again, not fair, right? So you have this tension. Right, you have this tension. So some people are like, proof of stake is not going to do that. We're going to have to do something else, right? Then other people are like, no, proof of stake doesn't work. And so there's a debate. And there's some organizations do proof of stake, and some don't. They still don't do proof of work. And then Ethereum is transitioning from proof of work to proof of stake. They're supposed to have done it a long time ago. This stuff takes time, right? So we don't know which. There could be another innovation that disrupts that proof of stake proof of work concept too. Right? Okay. So you sort of we already went through the hashing puzzle. Here's the data that doesn't change. Here's the nonce that changes. You're going to set the hash value to be a bunch of zeros. You specify how beautiful that is, right? So once the correct nonce is found or guessed at, right? Then basically you combine that. Now here's the solution. Now suppose Mark won the contest, and he found a nonce that you get a bunch of zeros in the hash value, right? So there's maybe 8 zeros in a row. He's going to broadcast that to the network. He's like, "Hey guys, I won!" And we're like, "What? No way! 12.5 Bitcoins!" And so he sends it out to everybody, and then everyone's like, "Well, we need to check if he did it correctly." So how do we check? You do the same. You have the data. You see if you get the same hash value. That's right. So he gives us the answer, he gives us the data, he gives us the nonce, and all we have to do is check. We just put it in, send it through the SHA-256. If the hash value is correct, so like, okay, you won. Take it, right? And then we all sort of agree, okay, fine, put it on there. Inside the block, he gets his coin-based incentive. Right now it's 12.5 Bitcoin. Okay, he gets that. But usually what happens is that one computer is not strong enough, then you allow your computer to be part of the pool. And the pool is getting all these different computers and using all that sort of power. And so the pool has a pretty good chance of winning this stuff. Once the pool wins, then it distributes out all these fraction of Bitcoins, right? So like every time your pool wins, how many Bitcoins do you get?
Well, it's doing about, about 500 split hashes a day.
500 Satoshis, okay. So a Satoshi is a million Bitcoin, or I think it's a small denomination that you can transact. Well, 0.000, I don't know how many zeros are. So basically, it's so small. I think it's 1 over 100 million or something like that. But that's a Satoshi. So you're getting about 500 Satoshis a day, per day, and that converts to how many dollars?
Oh, well, that's like, whatever, 30 cents a month.
30 cents a month. You make it 30 cents a month. It's not bad, right, on your personal computer. That's not bad. Electricity. It's already coming in. So it's not, that, no one's gonna quit their day job anytime soon. You can do it at the industrial level. So, if you're interested, there's a publicly traded company called Riot, R-I-O-T, Riot, and they, one of the guys, the COO, I know this guy, we're gonna try to do something together, but he said, oh, I'm gonna go take this job at Riot, and I said, what's that? It's like this small cap, publicly traded company that pivoted itself from bioengineering or whatever they were doing before into Bitcoin and crypto mining. They generate about 150 Bitcoins per month. So you can actually go to their website, you can actually see the mining operations, you can see what it is mining operation looks like, based up in Canada. That's where it's for. But all right. So we did that. Oh yeah, now this is a summary. Let's look at something fun here. So now we're going to go here and we're going to go to the first. We're going to go first